On the screen is the end of a number, not the whole number, only its last 10 digits, the ones that would sit at the far right if you ever wrote it out. They run 2, 4, 6, 4, 1, 9, 5, 3, 8, 7. The last digit is a 7, and we know that for certain. What we cannot do is write the rest of it. This number is so large that its digits would not fit on this screen, or in this room, or anywhere in the observable universe. There are about 10 to the 80th atoms in everything we can see through every telescope, and if you wrote one digit on each atom, you would run out of atoms almost before you had started. And yet the ending is fixed. We can compute the last 10 digits, the last 20, as many final digits as we have patience for, and they never shift by even one. The same 10 digits sitting on the screen now would still be there, untouched, if we asked for the last 100. So here is the situation worth sitting with. There is a single, specific whole number whose size is past any comparison a person can make, and whose ending we can read off exactly. The front of it is hopeless. The back of it is settled. This is Graham's number, and by the end of this video you will be able to work out its last digits yourself. To see why the front is hopeless, we have to try to build the number, and ordinary arithmetic gives out almost at once. Start tame. 3 times 3 is 9. 3 to the third power is 27, which is just 3 multiplied by itself 3 times. Notice that it already ends in a 7, and hold on to that because it comes back later. Nothing alarming yet. Now stack that idea on top of itself. Write 3, raised to the power of 3, raised again to the power of 3. You read a tower like this from the top down. The top 2 3s make 27, and then the whole thing is 3 raised to that 27th power. Work it out and you get 7.6 trillion, near enough. 7 trillion, 625 billion and change. A 13-digit number out of 3 small 3s and 1 extra step of stacking. There is a clean way to write these steps due to the computer scientist Donald Knuth, and it is worth meeting because the whole construction leans on it. 1 arrow means a single power. 3 arrow. 3 is 3 cubed, 27. 2 arrows means a tower of powers, stacked. 3 arrow, arrow 3 is that 13-digit number we just built. The rule for each new arrow is always the same. Take the operation you just had and repeat it. Addition repeated is multiplication. Multiplication repeated is a power. A power repeated, stacked into a tower, is 2 arrows. And the third arrow is where the floor drops out. Add a third arrow. 3 arrow, arrow, arrow 3. This tells you to build a power tower of 3s, and the height of that tower is the previous answer, 7.6 trillion. So you are stacking 3 on 3 on 3, climbing upward with 7.6 trillion 3s in the stack before you stop. It helps to picture how tall that is. Suppose each 3 were printed 1 centimeter high, and the whole tower stood up as a single column. It would reach about 76 million kilometers into space. That is roughly half the distance from the Earth to the Sun. And this is the part people miss. That distance is not the value of the number, it is only the height of the tower you would have to climb and evaluate to find the value. The value sitting at the bottom has so many digits that the digit count alone is already past anything physical. Now add the 4th arrow. 3 arrow, 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 arrow 3. This is the first real rung of Graham's ladder, and mathematicians give it a name, G1. To describe G1, you take that sun-high tower and feed its idea back into itself once more. We have already left every quantity in the physical world behind, and we are exactly 1 rung in. Graham's number is 64 rungs in. Here is how the ladder climbs, and it is the step that breaks your intuition for good. We have G1, which is 3, then 4 arrows, then 3. To get the next rung, G2, you keep the 2 3s on the outside, and you change only the arrows between them. There were 4, now there are G1 of them. Read that slowly. G1, that already unimaginable rung, the tower fed into itself, has become nothing more than a count of how many arrows you write down. Every single arrow was a jump to a higher kind of operation. and you are asking for G1 of those jumps, laid end to end. Then G3 uses G2 arrows, G4 uses G3, and so on. You repeat that 64 times. The last rung, G64, is Graham's number. Every step launches the number into a whole new category of bigness, the way a stacked tower is a different animal from a plain power, and it makes that jump 64 times over. There is no scale anchor I can hand you here, no cosmic quantity to point at, because every cosmic quantity was spent before we finished the first rung. That is the honest position we are in. The size is beyond us by design. It was built to outrun any description at all, which makes one question much sharper. Why would anyone build such a thing on purpose? Nobody set out to invent the biggest number they could. This one fell out of a genuine problem, back in 1971, in work by Ronald Graham and Bruce Rothschild. The problem is about connections. Picture a cube, but allow it to live in many dimensions so that it has a great many corners. Draw a line joining every pair of corners, and paint each line one of two colors, red or blue, in any pattern you please. The question Graham and Rothschild asked is whether you can always find 4 corners that lie together in one flat plane, with all 6 lines joining those 4 the very same color. 4 points in a plane have exactly 6 lines running between them, so the demand is that all 6 of those come out matching. It turns out that once the cube has enough dimensions, you cannot dodge it. A single-colored flat foursome is forced, no matter how cleverly you color. To prove that, they needed an upper limit on how many dimensions are surely enough, and the limit they could pin down was gigantic. A few years later, Martin Gardner laid out a clean, even larger version of that bound in his magazine column, and that is the version that became known as Graham's number. In 1980, the Guinness Book listed it as the largest number ever used in a serious mathematical proof. One more honest detail. The true answer to the cube problem is now squeezed between 13 and a ceiling far, far smaller than Graham's number. So the famous giant was never the answer. It was only a ceiling, and a much lower ceiling has since been found. Graham's number stayed famous for its sheer size, and for one other thing it quietly allows. It lets us read its own ending. The front of Graham's number is beyond reach. The back of it is a different story, and the whole reason is a small pattern that repeats in the powers of 3. Watch only the last digit as you raise 3 to higher and higher powers. 3 to the first is 3. 3 squared is 9. 3 cubed is 27, ending in 7. 3 to the fourth is 81, ending in 1. And then it comes around again. 3 to the fifth is 243, ending in 3, right where we started. The last digits run 3, 9, 7, 1 and repeat, with a period of 4 on forever. So the last digit of 3 raised to some power is settled entirely by where that power lands in the cycle of 4, which is just its remainder when you divide by 4. The exponent can be astronomically large and it makes no difference, as long as you know that one small remainder. Now Graham's number is 3 raised to an enormous power, and that power is itself a tall tower of 3s. A tower of 3s is an odd number, and an odd power of 3 divided by 4 always leaves a remainder of 3. So 3 raised to that power ends exactly the way 3 cubed ends. It ends in a 7. You can check the idea on the small tower we already built. 3 to the 3 to the 3 is 3 to the 27th, and 27 divided by 4 leaves 3, so it should end in 7. Sure enough, that 7.6 trillion ends in a 7, and it works one floor higher too. 3, arrow, 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 3, the sun-high tower, is still 3 raised to an odd power, so it has to end in a 7 as well. Every tower in this family does. The same reasoning, not changed by a single word, hands us the last digit of Graham's number. One digit is a nice trick. The good part is that the same idea, pushed a little further, gives as many final digits as you want. To get the last 2 digits of a power of 3, you watch them cycle instead of just the last one, and that cycle has a period of 20. So now you need the exponent's remainder on dividing by 20 rather than by 4. The last 3 digits march in a longer cycle again, and cost you a little more of the exponent. Each extra digit you ask for is paid by reading one more layer of the tower, and even then you only read that layer through a remainder, never in full. And here is the fact that makes the whole thing work, the one piece to keep if you keep nothing else. Once the tower of 3s is tall enough, piling more 3s on top of it does not change the bottom digits at all. The top of a tall tower simply cannot reach down and disturb the tail. So even though Graham's number carries unthinkably more 3s in its tower than we could ever write, all those extra 3s are silent. The last 10 digits were already decided by a tower just a handful of 3s tall, and every taller tower, Graham's number included, ends in precisely the same 10. That is the reason the ending is knowable while the size is not. The bottom of the tower settles early and stays put, and the top climbs off past the universe, contributing nothing to how the number ends. So let us read it off. The last 10 digits of Graham's number are 2, 4, 6, 4, 1, 9, 5, 3, 8, 7. It ends in a 7, exactly as we argued, and the 9 digits standing in front of that 7 are every bit as fixed. Do you want more of them? The last 12 digits begin 2, 6, sitting just in front of those 10. The last 20 come out just as easily, in a small fraction of a second on an ordinary laptop, and they are correct for the real Graham's number, all 64 rungs of it, because not one of those digits ever leaned on the height of the tower. Run the same short calculation on your own machine, and you would land on exactly the same string. We are exactly in the strange position this video opened with. We know the end of this number to as many digits as we care to compute, and we will never ever know the front. The count of its digits is past the number of atoms in the universe, so writing it out, or storing it, or printing it across every page that has ever been made is not just impossible. It is impossible by an impossible margin. The number is far too big to write, and at the same time perfectly clear about how it ends. Both of those are true at once, and that is the quiet surprise at the center of it. So that is the whole shape of it. Graham's number is built with Knuth's arrows, where one arrow is a power, a second stacks a tower, and each new arrow repeats the last. Its rungs climb 64 times, and each rung hands its own value to the next as a count of arrows. It came from an honest question about coloring the connections of a cube, as an upper bound that has since been beaten far down. Its size broke the record books and outran every physical comparison we own, and its last digits sit there, fixed and checkable, for two small reasons. The powers of 3 cycle through 3, 9, 7, 1, and the bottom of a tall tower stops listening to the top. The last digit is a 7, the last 10 are 2, 4, 6, 4, 1, 9, 5, 3, 8, 7, the same 10 we started on. If there is one thing to carry away, it is that being too big to write and being unknown are not the same condition. We can be completely certain about a part of something we could never hold whole, and if Graham's number feels like the far edge of large numbers, it is not even inside of the edge. There is a number called tree of 3 that makes Graham's number look like a rounding error, and it grows out of a simple game played with colored seeds. That one is for another day.